welcome to this lecture number 5 in the row of 13 lectures in the introductory statistics class that you're taking. Now, as you've seen maybe from my message from last evening, I decided to point you towards a couple of stories about one of our major Danish companies, if not the major Danish company, Novo Nordisk, pharmaceutical company, with a large focus on insulin products. Also other stuff, good stuff, but mostly insulin-type diabetes treatment. My reason for doing it now is that they had a new drug approved by the US Food and Drug Agency. So a drug was approved for the American market, which makes the stocks go like this for many reasons. Just to make the point, I mean, the very low-key point is, what makes Novo Nordisk able to get such a drug approved on the American market for billions, $1 billion Danish kroner decision, is because they did some data collection, and they did some statistics, and they did some hypothesis testing to make the decision that this is a good product. And they convinced the FDA about this based on the data and the analysis of the data that they supported and sent to the FDA, right? That's how it works. So the conclusions are made, the decisions are made based on statistical analysis of data collected for the purpose. So it's at the heart of making these billion-dollar business decisions to be able to do the right stats and the right hypothesis test, which we are going to learn today. There is another link to another study, so-called phase 3 clinical study, where they say, sorry for the Danish, but let me just quote a little bit. They quote some results. It's a promising new drug that they would probably hope to get approved in a year from now. They report some results, and a percentage of people who was treated with it had a good response. That's a short story. They had a lower level of their blood sugar. It's supposed to be not too high. And for instance, the weight loss of a person on 95 kilos when you use the drug like in a specific way was 5.6 kilograms versus 1.8 kilograms with some people doing something else, using a drug from a competitor company, in this case, I believe. So they show that they are better than the others. They make a decision. I see that these data tell me this, these data tell me that. I decide that this is better than that, and I do that according to the general scientific principles for how to do that we are all using, and that I'm going to teach you now for the first time in your lives. So it's not only science people who use this, it's the business people out there who use it again and again to make the right decisions about the product they do. Now I talk about pharmaceutical products. It could just as well be cars or anything else that are being developed based on the same principles. So, we should learn about the hypothesis test, which is the new statistical tool today compared to last time. Last time we talked about the confidence interval, and we're going to touch on the relation between those two tools, of course, because there is a relation. The confidence interval. If I should choose one, I think I mentioned it. If I should choose one out of a pure intelligence, sort of gut feeling, doing something for the world point of view, if I should choose between the confidence interval and the hypothesis test that I'd learned to you now, today, I would go for the confidence interval every day, all the time, anytime. Because that's the intelligent, that's the more intelligent thing, actually. However, I accept the fact that we need the we need the hypothesis test because we need to make decisions. I can give results of like a confidence interval. That's a nice and academic result. Here's what I compute, and here's my interval. Use it for whatever you want to use it for. That's the kind of, if you that you can do. You can give the confidence intervals to someone else and don't make any decisions. But hey, someone is going to make the decisions. Should I use this or should I not use it? Should I recommend this or should I not? Should I go forward with this in Novo Nordisk or should I not? So we need a tool to support decision making. And that's the hypothesis test. Here's the first version of it. To be in a context where we can deal with it, with the tools we have learned so far. Let's think of a sleeping medicine, a drug that we can use repeatedly so that we can have the same persons trying both drug A and drug B, right? So we can have person 1 try both A and B, and as it appeared, the B, that's how we should interpret these numbers, the B drug gave person 1 1.2 hour more sleep than the A drug, right? So B is better than A for that person. That's how we should interpret the number here. Also, so for person 2, 3, all of them actually, for all of them we saw an improvement of B related to A. But can we decide, can we conclude that we have proved that B is better than A, and how should we prove that? Here it comes. Now I have this slide where basically I give you the results and then we will learn how to achieve them. Right? So it's the same kind of structure as I've used a couple of times. The new way that we're going to put things is this. We are going to talk about a hypothesis, and we're going to talk about a null hypothesis in this case. When my purpose, and if I were the drug company producing drug B and trying to test it versus A and trying to prove to the world that my B product is better than A, so please approve it, right? And please use it. That's the argument after you have gotten it approved, and you have to convince people to use it also. I put up the null hypothesis, which is in a way the opposite. I say, hey, let me, as a sort of statement, claim there is no effective B, right? It's the same in relation to A, relative to A. B is not better than A. They are the same. Nothing has happened. You haven't come up with something new. That is the null hypothesis that I, as a company, would like to falsify, right? I would like to prove this null hypothesis wrong if I were the company trying to document that B actually works better than A, right? So that's the thought. I would put it like that. Computationally, I have gone nowhere since 4 weeks ago, right? Computationally, it's just one column in my Excel sheet, and even only 10 numbers here. So computationally, we know what to do. This is the only tool we have. We can compute the mean and the standard deviation, right? I would say that the mean would express how much better on average is drug B than drug A, right? 1.67 hours of sleep. And the standard deviation of these improvements is around 1 hour, 1.13 hours. It's not the same, this improved B improvement for the people. It's different from person to person, of course. And here it all comes. What we are going to learn to do is to answer the following. And I'd like you to get used to think like that. And I think it's a natural way of thinking if you think about it. Let me try. We would like to evaluate whether the data we get, this is the data, this is data, is that really in line with, in accordance with the null hypothesis, or is it in opposition to the null hypothesis, right? If I had basically an average of 0.1 hour, basically no real improvement, then my data would be in accordance with the null. right? So probably that would not prove B better than A. If my improvement was 12 hours, right, knowing what the scale of sleep per night is, if that's the scale, we were, whoa, probably all of the guys had 10 or 12 hours improved sleep. Basically, they would have come from 0, and now they sleep all night. Then, of course, yes, there is an improvement of B versus A. We have to find this fine critical level of where to distinguish between what is not approved and what is approved, right? That's what we should do. We have observed an average sleep improvement of 1.67 hours. The null claims 0. The way we're going to do it is to look at the data from the null hypothesis. So we put ourselves in the null. Let's assume that B is not better than A, just as a thought experiment, right? As an assumption, as a thought. If there is no difference, would it then be likely still to see 1.67 hours? Is that likely or unlikely, right? Is the data far away from my null? Right? That's what we are trying to find out. If it's close to my null, then probably I cannot prove anything interesting. If the data is far away from my null, whoa, yes, I have proved that B is better than A, right? I put this difference between the data and my null into a probability, because we learned also last time that a mean like that can vary from time to time. So we don't know. We cannot just say yes or no, but we can measure it by a probability because we know how the mean distributes itself from time to time, right? So this is the new thing. We're going to compute what is the probability that we go as far away as 1.67. That's one way to put it. Is that likely or unlikely? In this case, it only happens 1 out of 1,000 cases, right? 0.001. So this is the probability to see 1.67 or something just as weird as that, just as extreme as that. We use this, we conclude that this is a pretty unlikely event, right? It's pretty unlikely to see such a clear improvement on average of 10 under the assumption that B is equal to A, right? So what do we have to conclude? We have to conclude, well then B must be better than A. We have falsified the null hypothesis. We have falsified this statement that nothing went on, that they are the same. I have proved B better than A. This is the hypothesis test by the p-value, right? And I'm going to teach you how to do all this. So that was the first part, the introduction.